Don't worry. Don't worry. I'll try to do something today. Today. I'll have a look and see what I can do today. Yes. In fact, if you give me your number, I'll text you. Be the best thing. What? Do I have Ruby's number?
I have your number. Oh, what? Emergency.
But I don't have his number.
Let's try him.
Alright, fine. Let me save your name when you call. Cute Wookie. My wife would want to know why I have somebody in my phone book called Cute Wookie. Reject.
You got?
I got it. Save. Wookie. Okay.
Simple. Make it simple.
First name Wookie. Last name. Please. Yeah. Dude. I'll text you.
Okay.
I wanted to do it today, but the stupid photocopier's broken again, so I'll have to wait until they fix it. So maybe I'll... Huh? It's broken. Yeah, there should be someone, I don't know, there should be someone out. Sometimes, believe it or not, sometimes when it gets this hot, it actually affects the photocopier. Because the photocopier already gets very, very hot. So when it's very hot outside and it gets very hot, it sometimes just says no, too much. Alright, let's have a look. Physics. Yeah, so we're just going to do the tutorial on the Kepler's law. What's wrong with you? What? Yeah. Goodness. I think we could close the other blind a bit more as well. Ah, come on now. Not all of us are from the Middle East, okay? How is there... What? That's not... Is it racist to say the Middle East is hot? No. You just wanted to say it, yeah, okay. Yeah. How is Ramadan going today? It must be tough. Are you doing Ramadan? Yeah. Is it tough, or are you used to it? This is.
Yesterday was tough.
Yesterday was tough. What was different about yesterday? Just yesterday was tough.
Do you want to drink?
Oh.
Yeah. She can't have any food or water.
Wait.
I'm not having Ramadan.
Is it just the food way? Or food and water? Food, okay.
Not drink. Drink? Is okay? Drink and smoke?
It's not even a religion. Why?
That's right.
I don't think you smoke, do you? No. So that's something you haven't had to give up then. You would be the same? Yeah, so that's one thing you don't have to give up then. Can't smoke and can't swear as well. Yeah.
Maybe get some medicine.
Huh? Medical? Oh yeah, okay. And maybe you could. Anyway, let's have a look at this one now. How did we get on with this one? I should say that I made this question to look a little bit like a section B question on fields. What they sometimes do in the exam for the fields is sometimes it's like the whole question is electric and magnetic fields, or sometimes it's like half electric, magnetic, half gravity, and sometimes it's all gravity. So this is what a question might look like if it was just a field question on gravitational fields. Okay, so let's have a look here. Estimate the mass of Mars. So what do we want to be using to get the first one here? Well, actually, let me just draw what we have. So we have Mars has 2 moons. So we know there's Mars and there's the moon, and we know the distance and we know the orbit time. So we know the time here and we know this distance here, and we know the radius of Mars as well. Okay, so what should we do if I want to know the mass of Mars? Which formula should I use?
People doing this, how about change this angle, this TV angle?
Oh,
It's hard to see.
is that okay?
Yeah, it's okay. Better than.
That's okay? Yeah. Right, what formula do I need here? Yeah, t squared equals 4 pi squared over gm or cubed. So therefore, what was I looking for? The m, wasn't it?
Yeah.
The m equals 4 pi squared or cubed over gt squared.
Yeah.
Okay, so let's just take out the calculator here. 4 pi squared, what's the radius?
9380 times 10 to the 3.
And then the g is constant number 39. And what's the t?
7.65 by 3600.
So that's the mass.
No, you have to skip. You need to
Oh,
skip.
excuse me. Thank you. That's the mass.
Of course.
Right, let me just save that. I'll put that as an A on my calculator. Okay, sorry, did you get that number? Yeah? Is it okay? Yeah, next part? Let me just write this down. 6.44 times 10 to the 23 kilograms. Okay. Right, part 2. How fast? Right, so I think I'll just go with V equals omega r, which is 2 pi r over t. Okay, let's see what we got here. 2 pi, what's the r?
579380 10 by 10 to
Yeah, and then 7.65
the
times 3600. So the V is 2.14 kilometers per second. I'm going to store this answer as B. Ah, it's gone. Hold on, come back. Uh-oh. Shift, store, B. There we go. Okay. That's okay? Yeah? Right, part 3. Phobos radius can change by 10%. What is the fastest and the slowest? So, we have our formula V1 R1 equals V2 R2. Yeah? So you could say V2 equals V1 R1 over R2. And what I'm picturing is, I'm calling this one here the V1. So let's do the V2 is the maximum speed. So it would equal my answer for V1, my radius for V1, and then my radius for what would happen with my radius if I wanted to be going fastest? Less, smaller. How much smaller?
10%.
10%. So in fact, a quick way to do that is just to multiply by 0.9, 0.9, the old radius. Because 0.9 of a number makes the number 10% smaller.
Yeah.
So in fact, I can cancel those there, and my answer is just going to be v1 divided by 0.9.
Yeah.
So I can say the maximum velocity, so I still have this on my calculator, I just divide by 0.9. So it'll be 2.38 kilometers per second. And you can do the same thing for the minimum. What happens to the radius if you want the minimum? Bigger. How much bigger? 10% bigger. How do you make a radius 10% bigger? You multiply it by what? 10% bigger. 1.1.
Yeah.
Make something 10% bigger. So in the same way, I'll divide by 1.1 and I'll get 1.95 kilometers per second. That is the slowest the moon will be traveling at. Is that okay?
Can you like just add or subtract 10% and use other form, the normal form?
Oh yeah, like you mean for the radius? Or when you say add or subtract 10%, add or subtract from the radius, correct? Yeah. Yeah. I'm just taking a shortcut here, but you're right, that would be totally fine. Did you not get the same answer?
Maybe it's mathematical.
How off is your answer?
It's 1,000.
Oh, yeah, double check that calculation, yeah. Okay, next part.
Yep.
Yep.
Density.
Density of Mars, right. Think back to materials and mechanics also. What is the formula for density? Mass over volume.
Yeah.
Now we've worked out the mass, and what's the formula for volume? Yeah. 4/3.
I.
Yes.
Yeah.
Yes. So I saved the mass as answer A, I believe. So 4/3 pi r cubed, and the radius is, what's the radius again?
3390.
Dun dun dun. 3,944 kilograms per meter cubed. That makes it about 4 times denser than water. Because remember, water is 1,000. So it's 4 times denser than water. Okay. Next one.
Field strength.
Yeah, so what's the formula for field strength?
G equals, what was that?
Gm
over R.
or squared? Yeah. Okay, so I still have my M. It's I said for on Mars, didn't I? Or on the moon? On Mars, isn't it? So I have that saved as answer A. And I keep asking, I'm sorry, what's the radius? 3,390,000. So that's actually quite small when you compare it to Earth. 3.74 newtons per kilogram. You know, that's less than half of what it would be on Earth. Yeah? It's okay? Oh, not part 6. I'm using letters.
That's okay.
Should have been an F. Part F. What is the altitude of the parking orbit for a probe around Mars? So for Mars, park in orbit, what is the time? Now it's not 24 hours because on Mars a day is 24 hours and 40 minutes.
Yeah.
So it'll be 24 times 3,600 plus 40 minutes times 60 seconds. So let's just work that out first.
Okay.
88800. Okay, now Kepler said that T squared equals GM. No, I've got that backwards. Sounds like 4 pi squared over GM or cubed. And we're looking for the R.
Yeah.
So according to Kepler, R should equal cube root GM T squared over 4 pi squared. Yeah?
Yeah.
Okay, let's see. I saved this as A. This is 88800. Now, that is the distance from the center of Mars to the satellite for park in orbit. But I was being a little bit sneaky in this question.
This is alternative. You have to minus.
Yeah, because I said altitude. Altitude is measured from the ground. So I have to subtract the radius. So what is the radius to subtract?
3390.
3390000. Too many zeros?
I think something wrong.
Say again. 3390000. Now come here. What did I do?
Yeah.
Thank you. Thank you. Minus 3390000. And let's divide it by 1,000 to make it kilometers. 17,082 kilometers.
So the first R we got is the distance from
Center to satellite. Yeah. I subtracted the radius because I wanted the height, the altitude. I just did that to mess with you, that's all. Is that okay? Yeah? It's okay? Right, what's next now? G, is it?
Yeah.
What's the field strength on the probe when it's in the parking orbit? So let me just go back here a moment to this answer, and let me just save that as C, because I feel like I might need that. Okay, so what's the field strength? Well, we wrote the formula down earlier. In fact, maybe I still have it here on the calculator. No, I can't go that far back. It is G times M, which is answer A, all over R squared, which I just saved as answer C on my calculator. So, the field strength. Before we calculated, what was the field strength on the surface? It was about 3.7 or something? So, are we expecting more or less in a higher orbit? Yeah. In fact, it should be a lot less. Like, because you're very far away. Yeah, 0.102. I believe, no, it's not, and I believe I used the right or in that formula. Why, is your answer different?
center?
Yeah. Yeah. Oh, did you use the height?
No, I use radius and density.
Yeah.
How do you use the absolute value?
That's the... Huh? I'm confused about what the problem is. So, maybe we're saying the same thing. What I did... when I say radius, what I mean is this... I use this. But what she was saying, Audrey, was that she used this plus this. You know what you're saying? Yeah, of course. That's what I'm saying, yeah. But we use this. We don't use this by itself. Yeah.
You use on H.
No,
You use C.
Yeah, C is this.
It's not there.
Yeah, because
C
I...
is altitude.
No. I say this number
Yeah.
as C. Trust me.
I trust you.
Okay, thank you. Right. Is that one okay? Yeah. What is the kinetic and potential energy of the probe while it's in a parking orbit of Mars? That's interesting now. So the energy of the probe will be the kinetic plus the potential. The kinetic is a half mv squared, and the potential will be minus gmm over r. Now let's see what we know. Do we know this? Yes, and this, yes, and this, yes, and this, yes. I saved this as answer C.
No. That's it.
Yeah.
Right.
And this is the mass. Now we're talking about the moon, or are we talking about
Mars.
Mars? Yeah, sorry. So I saved this as answer A. I give you this as 100, and this is on my calculator. This is 100. The V we don't know. What I'll do is I'll change V into omega or. We could know it, yeah, and I'll change omega or into 2 pi over T, because we know the or and we know the T. It's at 24 point something. 88800. So this will be a half m 2 pi or over T squared minus gmm over or. Right, it's very cute, isn't it?
Yeah.
Like it's the cutest thing ever. Okay.
Like Hello Kitty.
Yeah, something like that. Or fairy doors. Same level of cuteness, really. Okay, so let's see. A half m v squared, which is 2 pi or over t, which is 88800, wasn't that it? Minus g fraction m times the other m over the radius. See how helpful those ABC store buttons are. So now in one click I get energy. It's negative, meaning it's trapped. You would have to give it energy to free it from the orbit. It's a very big number. Maybe we should use mega or giga. Giga's 9, isn't it? No, so then we should use we'll use mega then. Minus 105 megajoules. Mega. Yeah. No, micro would be great. Micro would mean it's very easy to free it. Okay. Yeah. Minus 105 megajoules. Yeah, that's quite a lot. So to free it from the orbit of Mars, you would need quite a lot of energy. Am I right in thinking, if anybody's calculated it separately, am I right in thinking that this is much bigger than this? Like this is a lot bigger? No, but I mean, if anybody calculated them separately, was that the case? No? let's just have a quick check. So let's see what the potential energy by itself is. Uh-oh. No. Oh no, they're about equal, because the potential energy is about minus 200 megajoules, so it means the kinetic energy must have been about plus 100 megajoules to leave us with about minus 100 megajoules. So actually, well, the kinetic and the potential are roughly equal, or no? I think what did I say this was? About 200 roughly. So this must have been about 100. Roughly, because we have to finish up with minus 100 megajoules. So actually I'm quite surprised by that. This is about half the size of this. I was expecting it to be less. Okay, do we have this written down? Is this one okay? Yeah? Okay, let me just close this video.